transistor. So power transistor will be classified into four types. So bipolar. So power power transistors are classified into four types. First one is bipolar junction transistor. So metal oxide semiconductor field effect transistor. So this is called MOSFET. And insulated gate bipolar transistor. That is called IGBT. And next static induction transistor. Okay. So power transistors are classified into four types. That is bipolar junction transistor. We are called as BJT. And metal oxide semiconductor field effect transistor. And this is called as MOSFET. And insulated gate bipolar transistor. This is called as IGBT. And static induction transistor. So today we are discussing power transistors. So next, bipolar junction transistor called BJP. So BJT has 3 layer and 2 junction PNP or NPN type. So bipolar means current flow in one device due to movement of both holes and electrons. Okay, so the BJP will transfer power from both holes and electrons. Okay, so that's why this is called bipolar transistor also we call. Okay, so these are the circuit diagrams for BJT. So here we have NPN type BJT and PNP type BJT. Okay, here we have collector, base, emitter. Okay, so this is the equivalent circuit for NPN type. So here collector and emitter and base will be there. Okay, so this is PNP type BJT. So here same collector, base, emitter will be there. Here PNP will be there, and this is the equivalent circuit for PNP type. Okay. So the difference between PNP and NPN means here the emitter current will be flows to base, and here PNP the emitter current. Okay, so here in PNP the current will be flowing from emitter to base, but in NPN the current will be going from base to emitter. So this is the difference between NPN and PNP. Okay, so in NPN the current will be going out, in PNP the current will be going into the base. Okay, so this is the VI characteristics of power BJT. So here we are taking NPN transistor circuit. Okay. So this is NPN equivalent circuit. So to determine VI characteristics, here we have taken NPN transistor. Okay. Here we are connected base. So here we are connected to base and collector to, so and voltage here we are connected, voltage will be VCC, and here we are connected voltage to the base will be VBB. Okay. So here the base to collector. So here the voltage will be VCB, and base to collector voltage will be VCE. Okay. Here the current flowing through IC, and it will be going to, and the current flowing through from base, these are all will be outing through the emitter. Okay, so here we have seen input characteristics, output characteristics of BJT. Okay, here the input characteristics will be drawn between VBE and the current IA. Okay, so here the curves will be like this. Here the applied curves will be VCN, VCE2. Okay, here the voltage between collector and emitter. So the voltage between collector and emitter will be obtained when drawing the input characteristics between base base current base current and the voltage between base and emitter. Okay, so VBE and IB, when we taking on x-axis the voltage will be VBE, and when we taking the current on base current on y-axis, so the curves will be curve will be here. So this curves will be called VCE. Okay, VCE and VCE1. Here VCE2 will be greater than VCE1. Okay, and these are the output characteristics. Okay, here we are taking the emitter. Here collector emitter voltage and IC. Okay, actually in input characteristics we are taking base and base to emitter voltage. Why? Because from input side we have base and okay, base and this emitter will be there. That's why. So we have drawn from base current and voltage obtained between base and emitter. Okay, and here output characteristics we are taking collector current and collector to emitter voltage VCE. So output current will be IC and output voltage will be VCE. That's why we are drawing graph between VCE and IC. So this is and when and up and obtained curves will be we have base IB. Okay, base current. So here first obtained curve IB equal to 0, IB1, IB2, IB3, IB4 and IB5. Okay, so here IB5 will be greater than IB4 and it will be greater than and so on, it will be greater than IB1. Okay, here at last we obtained current will be very high when compared to this. Okay, so these are gradually increasing the curve. Okay, so here at starting the leakage current will be flowing and this is called cutoff region and this is will be called saturation region. Okay, so this is the NPN transistor circuit and input characteristics and output characteristics. Okay, for BJT. Okay, so switching characteristics for BJT. So when you're taking a NPN transistor with resistive load. Okay, here the RB, RC will be applied and here voltage will be VCC. Okay, so here VB and here output voltage VCE and input voltage VBE. Okay, output current will be IC. Okay, here the input current flowing will be IB. So this is NPN transistor with resistive load. Okay. So when you're taking switching characteristics of power of BJT. Okay, when you're seeing switching waveforms power BJP for BJT, here base voltage. Okay, so the base voltage at starting will be obtained in negative mode. So gradually increase and going to positive forward action and it will be increasing gradually. And again when BJT will be turned off, then it will be going to 0 and it will be in reverse bias. The current will also flowing. Okay, so BJT will be bipolar type. That's why the current flowing both positive and negative. So here the voltage will be obtained here V1 and negative direction negative side will be obtained V2. Okay, here base current IB at starting the base current will be 0. Whenever it will be increasing the whenever we are giving input to base, then the base current will be flowing through circuit up to up to negative cycle. Then it will be reaching the reaching negative polarity IB2 and it will also conducting sometime. Okay, and then goes to 0. Okay, this is IB and VBE. VBE means so base emitter voltage at starting base emitter voltage also 0. So at saturation occurred 0.7 volts. Then the VBE will be going on increasing. Okay, so and it will be conducting. After that it will reach us to some point. So then reaching the some point will be 0 and it will be obtained minus of VB. Okay, in negative polarity the voltage will be obtained. Okay, and next V. Okay, here ICS. Okay, collector current. Okay, At starting, the collector current will be 0. So whenever we are giving a supply to base, then it will be going on increasing, and at saturation point it will saturate, and it will be constant at some point, and it will be reducing when the emitter base will be 0. Okay. So and it will be 0. Okay. And here the emitter to collector voltage at starting, the VCE will be charged. So that's why the voltage will be not 0. So here the voltage will be here, it will be there. Whenever the base current will be flowing, then the VCE will be discharging. So discharging means it will comes to 0. So up to this, whenever after when IB will be 0, then again the VCE will be okay. So then again it will be going. So these are the switching waves of power BJT. And next, safe operation area for BJT. Okay. Here forward bias safe operating area and reverse block safe operating area. Okay. So safe operation area for BJT and reverse block for forward direction, and reverse direction for safe operation will be seen in graph. Okay. So when you draw a graph between VCE and IC, here we are taking, so when when T1 is less than 25 degrees. So from this point, this is a safe mode of operation. And here in reverse bias direction, so here IB equal to 0, IB equal to 2 amps, and IB equal to 5 amps. So this will below this IB equal to 5 amps. So this is a safe operation of safe operation for BJT in reverse blocking mode. Okay. And next, MOSFET. So this is the symbol for MOSFET. Okay. So this is symbol for MOSFET. Okay. So power MOSFET has three terminals, drain, source, and gate. Okay. Here this is drain, and this is gate, and this is source. Okay. So power MOSFET. Okay. Power MOSFET has three terminals. So that is drain, source, and gate. Okay. This is voltage controlled device. Okay, gate circuit impedance is high. Okay, gate circuit impedance is high of the order of mega ohms. Okay, so the gate circuit impedance is high. So in mega ohms, so it will be very high. Hence, the gate can be driven directly from the microelectronic circuit. Okay, used in low power and high frequency converters. Okay, SMPS and inverters. Okay, so MOSFET will have three terminals: drain, source, and gate. Okay, so this is voltage control device, and gate circuit impedance will be very high. So it will be in mega ohms. Okay, so hence the gate can be driven directly from the microelectronic circuit. Okay, so MOSFET actually used in high frequency converters such as SMPS and inverters. Okay, and next, basic structure of N-channel power MOSFET. Here we have N-channel power MOSFET and P-channel power MOSFET. Okay, so this is basic structure for N-channel power MOSFET. Okay, we have three terminals per MOSFET: gate, drain, source. Okay, so here, so this is a equivalent basic structure of N channel. Okay, so this is basic structure. It consists of, here drain will be there and gate will be there. Okay, and here source. Okay, so this is N channel power MOSFET. So this is the drift region. Okay, here in N channel MOSFET here N. So N plus N here we have seen N plus plus, here N plus plus and here N plus plus. So and after that P and N minus N minus, and this is N plus and this is N plus subtract. Okay, this is the current path. Okay, drain, when you are draining the MOSFET. So this is the current path. Okay. So this is the basic structure of power MOSFET. Okay. And here we are connected load between the drain and source. Okay. So MOSFET transfer characteristics. Okay. So the transfer characteristics will be obtained and between the VGS and ID. VGS means voltage between gate and source, and ID will be drain. Okay. So this is the MOSFET equivalent circuit for obtaining okay, transfer characteristics. So output voltage VDD, here ID drain. Okay, drain current versus VGS. So output current versus input voltage, the obtained will be VGS will be, curve will be like this. Okay. And next, MOSFET output characteristics. Okay. These are the MOSFET output characteristics. Okay, so output characteristics means, so drain source voltage. Okay, so drain source voltage and drain current ID. Okay, drain source voltage and drain current voltage. So these curves will be like this. Okay, it will be going here. We have seen these curves. The curves will be like this. Okay, so here active region will be there. Okay, so drain source breakdown voltage will be obtained here. Okay, and this is the active region. Okay, and MOSFET switching characteristics. So switching characteristics, when you drawing a, so here VG, so when you taking time on x-axis and y-axis, we have voltages here VG. So the V1 will be at starting, the V1 will, so at gate, sorry, at gate voltage VG will be constant up to T1. Okay. So when you drawing the VGS voltage, VGS versus time. So the VGS means voltage between gate and source. At starting, it will be 0 and gradually increasing, and it will be constant up to some time and it will be decreasing. Okay, so here the increasing VGS1, VGSP and V1. Here at V1, the, so the VGS will be constant. Okay, this is time, and this is TDF, and this is TF. Okay, this will be off time. Okay, this will be rise time. Okay, so here ID, the current, drain current at after rising the VGS voltage, the T on will be going on increasing and it will be up to, so when it reaching the T1, it will be gradually decreasing and comes to 0 ID. Okay, this is the MOSFET switching characteristics. Okay, next, when you comparison between MOSFET and BJT. Okay, so actually BJT is bipolar device and MOSFET is unipolar device. It has low input impedance, kilowatts, but MOSFET has high input impedance. Okay, high switching loss, but lower conduction losses. Okay, lower switching losses, but high on resistance and conduction losses. Okay, current and controlled device. Okay, voltage here. This is current control device. BJT has current control device, but MOSFET will be voltage control device. Okay, negative temperature coefficient of resistance parallel operation is, okay, this is negative temperature coefficient of resistance. Actually, parallel operation is difficult. Parallel operation is difficult and current sharing decision should be used. But here it is a voltage control device and positive temperature coefficient of resistance. Parallel operation is easy. Here parallel operation is easy, but here parallel operation is difficult. Secondary breakdown occurs, but MOSFET there is no secondary breakdown. Okay, so available with a rating of 1200 volts to 800 amps. So this is available rating will be 500 volt to 140 amps. Okay. So BJT is a bipolar device and MOSFET will be unipolar device. Here we are using low input impedance. Here high input impedance and high switching losses and lower conduction losses. MOSFET has high resistance, so lower switching losses but high resistance. Okay, and conduction losses will be there. Okay. And this is BJT as a current control device. MOSFET has voltage control device. Negative temperature coefficient of resistance parallel operation is difficult. Okay, here positive temperature coefficient parallel operation is easy. Okay, secondary breakdown occur and secondary breakdown does not occur. Okay, so with rating of 1200 to 800 amps. Okay, here 500 volts and 140 amps. Okay, so the comparison of BJT and MOSFET. And next, IGBT. IGBT means insulated gate bipolar transistor. So the insulated gate bipolar transistor means IGBT. So combines the best qualities of both BJT and MOSFET. So IGBT will be occurring both best qualities of BJT and MOSFET. So has high input impedance as a MOSFET and has a low on-state power loss as in a BJT. Okay. So high input impedance in MOSFET and has a low on-state power loss as in BJT. So other names for MOSFET, metal oxide insulated gate transistor and committee efficiency. Okay, COMFET efficiency. COMFET efficiency means conductively modulated field transistor and JEMFET, gain modulated field effect transistor and IGT, insulated gate transistor. These are the other names for IGBT. Okay. IGBT occurring, so combining both best qualities of BJT and MOSFET. So in MOSFET has high input impedance, has a low on-state power loss as in BJP. Okay. So next, so this is basic structure of IGBT. Okay. So here this is emitter and this is collector and this is gate. Okay. So N channel MOSFET structure. This is so N channel MOSFET structure will be like this. Same here. We have BJT has 3 terminals, that is gate, emitter, collector. So at we are taking same this emitter, collector, gate, and at this body we have P N minus, N plus and P plus. This is tracks, injection layer, and this is buffer layer, and this is drift region, and this is a body. Okay, this is N-channel MOSFET structure will be like this. Okay, so this basic structure of IGBT. Okay, so the basic structure of IGBT will be like this. Here collector, emitter and gate will be there. Here body region, this is a, okay, this is injection region. Okay, so this is subtraction or injection region, buffer region, drift region, body region. Same body region, drift region, buffer layer and subtract layer. So this is body region and this is drift region and this is so body region, buffer this is buffer region and this is drift region, and at the last we'll have injection layer. Okay, so equivalent circuit of IGBT will be like this. Okay, so we have here we have seeing this is a transistor and this is a MOSFET. So this will be like this. So this MOSFET will have connected resistance and this will be connected to BJT. So this is IGBT. Okay, here transistor to the, here MOSFET will be there. So when you connecting this, okay, this is equivalent circuit of IGBT. So basic structure of IGBT means, so here emitter, gate, collector, here transistor, BJT, emitter, gate, collector, and this side will have MOSFET also will be there. So this is P plus subtract N minus and N plus and P minus. Okay. So here J1, J2 and J3. Okay. This is a J1, J2, J3 junctions will be there. Okay. So this is basic structure of IGBT. So the IGBT will occur combining BJT and MOSFET. Okay. So equivalent circuit of IGBT will be like this. Here PNP and NPN transistor, and here we have N channel MOSFET. Okay. Here we have resistance will be connected, and this is emitter NPN and PNP, and this will be connected to N channel MOSFET. Okay. So VI and the transfer characteristics of IGBT. So the VI and transfer characteristics will be obtained when you're drawing a graph between VCE and IC, and VBE and IC. Okay, this is the transfer characteristics. So it will be VCE1, VCE2, VCE3, VCE4 will be obtained. That will be VCE4 will be greater than, VCE3 will be greater than, and VCE1. Okay. So here VBE versus IC. So the curve will be like this. Okay. So next, switching characteristics of IGBT. So the switching characteristics will be drawn VGE. So here the VGE will be like this. So at starting it will be leakage mode, and it will be going on increasing, and it reaches a saturation, and it will be at a saturated point, and it will be decreasing. And here VCE versus time. So the characteristics will be VCE. So at 0.9 here we have 0.1 VCE. Okay, so these curves will be like this. Okay, so VC at one time VC equal to VCC. Okay, so these are the switching characteristics of IGBT. Okay, so applications of IGBT. So where we use applications of IGBT means DC and AC motor drives and UPS system and power supplies. Okay, drives for solenoid relays and contactor. So applications of IGBT means where we are using IGBT means DC and AC motor drives. So in motor drives we are using IGBT. So DC motor drives and AC motor drives we are using IGBT, and UPS system and power supplies. So in UPS systems, okay, so in UPS system and power supplying. So in power supplying also we are using IGBT, and drives for solenoid relays and contactors. Actually in relays and contactors we are using IGBT, and drives for solenoids. So we have to drive solenoids, we are using IGBT. Okay. So IGBT will have DC and AC motor drives, UPS system power supplies, and drives for solenoid and relays and contactor. Okay. And next, comparison of IGBT and MOSFET. Actually, in IGBT we have three terminals. They are gate, source, and drain. But in IGBT we have three terminals are gate, emitter, and collector. Okay. So MOSFET has high input impedance. IGBT also have high input impedance. Okay. So MOSFET actually will be voltage control device. IGBT also voltage control device. So the ratings will be, the ratings of MOSFET will be 500 volts and 140 amps. But in IGBT we have 1200 volts and 500 amps. So operating frequency is up to 1 megahertz, but operating frequency is up to 50 kilohertz. So with rise in temperature, the increase in on-state resistance of MOSFET is more pronounced than the IGBT. So the on-state voltage drop and losses are rises rapidly in MOSFET than in IGBT. So with the rise in temperature, okay, with the rise in voltage, the increment on-state voltage drop is more dominant is MOSFET, okay, than the in IGBT. So this means IGBT can be designed more higher voltage rating than the MOSFET. Okay, so actually IGBT will be occurred by combining best qualities of BJT and MOSFET. Okay, so in MOSFET we have three terminals. So gate, drain, source. Same in IGBT will have three terminals. These are gate, emitter, and collector. Okay, so in MOSFET also have high input impedance. IGBT also have high input impedance, and MOSFET will be voltage controlled device. Same IGBT also voltage controlled device. But ratings of MOSFET will be 500 volts and 140 amps. So here IGBT ratings will be 1200 volts to 1500 amps. Okay, so the operating frequency in MOSFET will be 1 megahertz, but in operating frequency in IGBT will be 50 kilohertz. Okay, with rise in temperature. So the increasing in on-state resistance in MOSFET is more pronounced than IGBT. Okay, so the rise in temperature. So whenever we are increasing a temperature, the on-state resistance in MOSFETs are okay. So than IGBT. So on-state voltage drop and loss rises rapidly in MOSFET than IGBT. So rise in with the rise in temperature. Okay, so here in IGBT, the on-state voltage drop and losses rises rapidly in MOSFET than IGBT. Okay, so actually in losses rises in MOSFET than IGBT. Okay, with the rise in temperature. Okay, so with rise in voltage, the incremental in on-state voltage drop. Here by increasing a voltage, the incremental on-state voltage dominant in the MOSFET than the IGBT. So this means IGBT can be designed more higher voltage rating than MOSFET. Actually, so the IGBT will be designed more higher voltages. Okay, so more higher voltage we are designed IGBT. Okay, so this is our topic today. Okay, so thank you.